Okay. Yes. Okay. So thank you for the invitation from the organizer of the workshop, and so I will try to discuss some of the work that I've been doing with several people. Actually, the works started very quite long time ago together with Giuseppe Policastro, and then. And actually, that work was based on pure spinous superstrings, okay? But then we understand that actually this framework can be extended in a very general way towards what is known as supergeometry. And so then we started to try to understand from a more mathematical point of view what was going on, okay? And then, let's say, so we wrote several papers, but actually one of the very first paper that we understand some of the important points together with Carlo Maccaferri, where actually we formulate a super Chern-Simons theory, Chern-Simons theory in really as an integral of some superforms. Superforms, and then later, together with Leonardo Castellani and Roberto Catenacci, we somehow develop more mathematical tools to understand these issues. And finally, so it was Castellani and Catenacci. And then finally, together with Simone Noia and Catenacci, actually, we developed a complete mathematical framework to understand these structures, and it emerges a beautiful high-infinity structure that I'm trying to discuss in this framework. So let me give you the starting point. Okay, the starting point was the following. Okay, so let me remind you how, for example, Chern-Simons theory it is formulated. So you start from a gauge connection A, which is just a one form, okay, on a given manifold. Maybe carry some representation in the joint of a group, okay, and then you define an action, which is the following form: is an integral of this ADA. Okay, plus also the interaction terms. So let's say, let me put a trace, and you have like a 2/3 A wedge A. And so you know that this is an integral of differential forms, and these differential forms, let me call it LL3, is a differential form on this manifold. It's three forms on these manifolds. With some properties, okay? But the interesting fact is the integral is done just as a form integral, okay? So this means when you calculate this object, it doesn't depend on the metric on the manifold, okay? So the idea is, okay, can I rewrite these expressions? Can I construct an expression equivalent to this in the case of a super Chern-Simons theory, or in the case of super manifolds? So let's try. I want to do the following. So instead of just a bosonic manifold, let's say a three-dimensional bosonic manifold, I want to replace this bosonic manifold with a super manifold, which means a manifold which has let's start with the easiest things is just adding two fermionic coordinates to this manifold. I use the following notation. I use just XA to denote the bosonic coordinates and theta alpha to denote the fermionic ones. Okay, so the index A goes to 0, 1, 2, and the coordinates alpha goes 1 to 2. Okay, so I have two fermionic coordinates parameterized in this super manifold. And in particular, locally, I can represent this just as a superspace, just a 3/2, but in general, I can consider a more general manifold. In particular, we consider, for example, some non-trivial supermanifold, for example, like a superprojective supermanifold, for example, in order to consider really a very general settings. Okay, but the point is now is how can I formulate an action, okay, which isn't just an integral on this manifold 3/2 on a given action here, in such a way that has the same property, namely has really doesn't depend on the metric on the manifold. It's just a form which can integrate it on the supermanifold and has all the good properties. Okay, and then I will show you that this framework can be applied for any quantum field theory, any supersymmetric quantum field theory, provides a very general framework for all these models. Okay. So the idea is the following. So if I want to really to integrate it on the supermanifolds, there are several discussions in the literature, and so the problem is the following. I want to integrate something which is a form on the supermanifold. So therefore, a form, okay, in a supermanifold can be written in this way. So first of all, okay, I can consider a form, okay, which is like which we know as a usual form. Okay, so this means I expand the form belonging to this space, omega, and so that would be a local expansion, a local expression in terms of some functions, x and thetas, and then there is an expansion of dx and dx, let's say a1, an, okay, and some expansion of d theta alpha 1, d theta alpha m, for example. Okay. Now, the total degree of this form is just the sum of the degrees. So this is just n one forms, these are m forms, so the total degree is just m plus 1. Let me put a p, so that this is just the p, which is the dimensions, the degree of this form. And in front of this, there is a function of x and theta. Okay. Now, if I really want to write down in a more careful way, so what I have to do the following. I have to put some indices here. So the first indices related to the bosonic coordinates as antisymmetric indices, but for the fermionic ones, okay, I will have some commuting indices. Okay, I can also put the wedge product inside in such a way that, say here, the product of d thetas are commuting variables, and therefore these indices are symmetrized. So this means there is no notion of a top form in this framework, okay? So for example, if I start from 0, so these are the 0 forms, okay? I construct the 1 forms, and then 1 forms are constructed in terms of dxa or d theta alpha. Then I will have 2 forms, okay, and so on, okay? But here there is no upper bound for this space, so I can construct any form of any degree out of this. So there is no notion, no, let's say, simple notion of a top form in this framework, okay? So, so therefore, I cannot really perform the same construction as in the usual Chern-Simons theory for super Chern-Simons. However, starting from some construction or even in string theory, so one actually introduced a new type of forms. Those are known as integral forms. And those are based on the following object. One introduced this quantity, which is just a delta function of d theta alpha, okay, which is the usual Dirac delta functions of d thetas, okay, with the property, for example, if I can compute the differential of this delta of here, this is equal to just the first derivative of delta functions and d of theta alpha, then turns out to be 0, okay? And I also use some distributional property, namely delta alpha, delta prime of d theta alpha, that will be equal to minus of delta of d theta alpha. Here, this alpha is not summed, it's just only the product of the same d theta times delta of the same d theta alpha, okay, of d theta prime. So every time I find a derivative of delta functions and it's d theta, then it increases, it removes the derivatives, it gives just delta, and of course I also have the the distribution property that theta alpha is equal to 0, okay? And of course, all the other distribution properties. In particular, if I have two coordinates, like in the case that I'm discussing here, the wedge product of two delta functions, okay, it's just an anti-commuting property, anti-commuting relation between those, okay, delta alpha. So they do anti-commute respect to the exchange. That can be checked in several ways, essentially by defining an integral of this object. Okay. So therefore, I'm constructing a new type of forms. A new type of forms are parameterized by the new number, which is known as a picture number. A picture numbers, okay, and this picture number counts the number of deltas, okay, the number of deltas that I'm inserting. So therefore, the complex of forms now is get very rich. So I will have a line which is called a picture zero forms. And this is just parameterized in this way, let's say P and 0, and it contains, so these terms, which is just the 0, 0 forms, and 1, 0 forms, and so on, up to any power of this, so there is no upper bound here, okay? So I will have also picture, in this case, picture 2 forms, okay? So the picture 2 forms, let me start from this point, okay? So I will have like, yes, 0, 2 forms. Sorry, I have put it, yeah, let me put it here. Okay, let me put it here, omega 0, 2 forms, okay? Then I will have omega 1, 2 forms, and then I can go over, okay? But at some point, okay, because of this antisymmetry of delta functions, okay, I hit just a top form, and this top form in this case is just /32, okay? Let me write down a local expression for this, okay? A local expression for the top form in this case is just is equal to just a function, okay, x and theta, and then we'll have like dx. In this case, there are three of them. Dx, so A, B, and C, epsilon A, B, C, and then I have epsilon alpha beta, delta of d theta alpha, and delta of d theta beta. Okay. Now, actually, one can check that indeed these expressions I wrote down here transform as the Berezinian of, and therefore it transforms correctly as the highest top form in these games. Okay, so this, and then afterwards, after this point, okay, there is no other form possible because this is represent a top form. In fact, actually, if you calculate d of omega in this case, this gives you 0, which is just the top form. However, because of this construction, however, you can go lower with your form degree because you can do the following. You can build some integral forms with the delta function, but with the derivative of delta functions. So I can have a derivative of delta function. So let's suppose that I put here just the derivative of delta function, d theta alpha, and derivative of d theta beta, okay, which means they are derivative of delta function, which count negatively the form degree, okay. So this means this object has a minus beta 2 form degree, and then if I multiply by the axis, okay, and the axis here, I also have some powers, as I said before, n powers. So the form degree, the total form degree of this object is just the number of bosonic ones minus the derivative of delta function appear here. Of course, here I can also put some delta here in front, but every time I get the delta here, and then the number of delta function saturates just the maximum number of fermionic coordinates. If I multiply by d theta with some delta function, either give you 0 or it decreases the form degree. Okay, so therefore, in this case, I cannot add any d theta here. Okay, so this means the following. So I can go lower here, so I can construct some negative forms here, negative degree forms, okay, 2, and so on. And here there is no upper, no below bound in this particular sector or particular complex of my space. Okay. Now here in the between, there are picture number 1. Of course, there are two types of picture number 1, because I can either have delta of d theta 1 or a delta of d theta 2. Okay, delta of d theta 1. So in this particular case, what I can do, I can build some forms. Okay, at picture number 1. Okay, but also here I can have any degree, because I can build a form of these types in this way. So I can have any derivative of some d theta 1, for example. Of course, I can multiply by the axis. Okay, but then I can also multiply by d theta 2 here, by some power of d theta 2, okay, m, for example. And then this means the total degree of this form, this is just n plus m minus beta 1. This is the total form degree, and so they will have a picture number 1 because there is one delta function involved, and the total degree is just the sum of bosonic plus the form degree coming from d thetas minus the number of derivatives active on delta function. Okay. It turns out the following. So there is another line of this complex which contains a form of this type, 1 omega 1, 1, and so on. Okay, and this particular complex has no upper bound, but also there is no below bound here, because I can go lower in this way. Okay, in this way. So I can move along these lines. I can move along the lines using the differential d. So if I use the differential d, I can move along these lines. Okay. So I can map and increase the degree every time I use the distributional properties in order to do that. Okay. So this one interesting aspect. So this full complex here of forms. Okay. It's now parameterized by two numbers. This is just the form degree, and the other one is just known as the picture number. And it's parameterized completely. Now, the fact that it is called picture number in, let's say, it reminds us the picture number in string theory, and indeed, actually, it is very similar. And then I will tell you why this is so. Okay. Now, however, one can ask if there is an operator which map transversally. So if we really can change the number of delta functions here. And now, okay, let me do the following. Okay. So now I can. Given these structures, so this means that if I really want to formulate an action and integrate on this supermanifold, let's stick to our example 3-2, I can do the following. So certainly here I have to introduce a forms which is just a top form type. Okay, so this is something that I can integrate. So this is an integral form, of course. Of course, the easiest way to do it is the following: take L3. Okay, L3, which is just a 3 form, okay, at picture number 0, which is a normal superforms that you can build in general, okay, and then try to see actually if you can do the following. If I use this one, I can try to do the following. I can try to write down my integral, okay, on a submanifold of a supermanifold, okay, of this L3. Okay, and then I can do the following. I can try to rewrite this expression as an integral, okay, of a 3-2, okay, by multiply this object by some forms, which I call it eta, which has a 0 and picture number 2. So namely, okay, this object here is just the Poincaré dual of the immersion of this M3 submanifold into M3-2. Okay, so namely, I can try to rewrite this integral as an integral on the full supermanifolds just by rewriting this action, which is just a tree form, as a tree form, however multiplied by a form which is a zero degree form, picture number 2. In such a way, the total degree of this form is just a 3, 2, and I can integrate it over this manifold. Now, of course, this is the easiest way to do it, because namely, I consider the situation where the integral forms which are integrated is factorized in the 3 forms and times an object which is 0, 2. Okay. Now I can build this object in a very simple way. One way to build is the following. Suppose you do the following, okay? Suppose you have a bosonic manifold, okay, and you want to immerse into a supermanifold, okay? And I do it in a very simple way. I add to this some fermionic coordinates, theta alpha, okay? In such a way, if I set theta alpha is equal to 0, I'm going back to my original manifold. So I immerse my submanifold inside of a supermanifold in a very trivial way, okay? In a very horizontal way. In such a way, if I set theta equal to 0, I go back to my original manifold, okay? However, if I set the theta equal to 0, this is equivalent to say also d theta alpha is equal to 0. Also the one forms in this case. So this condition can be written in this following way. Let me write down eta 0, 2 as follows. Okay, there is a theta 1 delta of d theta 1. Okay, or even better. Okay, I can write theta 1 and then a d theta 2 delta of d theta 2. And actually, this particular object, okay, so the Dirac delta function of a fermionic coordinate is just the coordinate itself. And this is just the Dirac delta function of d theta 1, theta 2, and delta of d theta 2. Now, this expression was introduced, I can also write down in I goes to 1 to 2 of theta I delta of d theta I, okay. Was also introduced in the also we learned this expression from this Pius-Spino's string theory, actually, where instead of d theta there are the Pius-Spino's lambdas instead. Now this object here, let's say this combination here, are known indeed as a picture change operator theta 1, okay, which is theta 1 of delta d theta 1. Okay. And this object, it is closed, dy is equal to 0. It is not exact, so it's different from something. And any variation of this object is the exact, okay, which are exactly the condition to define the Poincare dual. The Poincare dual, it is closed quantities, 0, 2 is equal to 0. It is not exact, 0, 2 is different from d of something, omega, okay. And any variation of the immersion of the manifold in the supermanifold, it is exact, okay. So then, okay, so if I use this particular eta, okay, it happens the following. Let me write down the action in this way, okay. So my action S, it will be just integral of m32. So here I have the action, which depends on x in theta, dx on d theta, times this object, pi, I goes to 1 to 2 of theta I, delta of d theta I. Now, of course, this is just a kind of a trivial integral, because if I perform the integration, the presence of the thetas project out theta equal to 0 from the Lagrangian, and the delta of the theta project out delta of the theta equal to 0. So then here, if I do the calculation, I'm getting back to my original manifold, and the action is computed for x, theta is equal to 0, dx, and d theta is equal to 0. And that actually should correspond to the component action. to the component action. So the idea is, okay, so, okay, can I do something better? Of course, I can change this quantity here by exact terms, okay? So I can replace this eta, 0, 2, I can replace it by this particular one with another one. Let me call it 0, 2, okay? And finally, I can write down my action in the following way. Slash 32, okay? The action is just 3, which is just a superforms in terms of x theta, dx and d theta, times a picture change operator 0, 2. This is quite general expressions, okay? Because now here I can change this picture change operator as I wish, okay? In order to obtain a different version of the same theory, okay? Now this works. Namely, I can change this without any change in the theory if the action here it is closed. Namely, if d of L 3, 0 is equal to 0. Okay, if this is closed, then I can change this by adding exact terms without changing the theory. Okay. Now it turns out that any supersymmetric models that we know, namely Supergeometries, super Versumino model, or super Chern-Simons, can be written in the following framework. Okay, namely, so. It is done in this way, okay. Suppose that I want to do it Supergeometries in 3 dimensions, d equal 3, n equal 1, okay, which can be written exactly in the same supermanifolds, 3, 2, okay. Then, okay, we know what are the spectrum of this theory. The spectrum is just a gauge field, okay, and then there is a gaugino. Okay, so, and then I can write down the actions. My action will, it is constructed in this way. First of all, you promote the gauge field to become a superfield, actually a super one form. A super one form means the following. You have an expansion along the axis, okay, I put A, sorry, plus A alpha d theta alpha, okay? So this is an element of omega 1, 0 in this framework, okay? Yes? So, genetic? Yeah, of course, okay. Yeah. Yeah, sure. You have to take into account boundary terms, okay, if you do this calculation, okay. Certainly, namely, so when you perform the variation of y, okay, you have to take into account boundary terms emerging from this, yes. I'm neglecting boundary terms for the moment, okay. Yeah, so namely, the idea is actually you can do it for general supermanifold, okay, and therefore take into account even boundary condition. We have not done the calculation in the case of, let's say, globally defined supermanifold, but certainly the framework has the power to do all these things. So what I'm doing here just only for local situation, okay. Yeah. Yeah, in this case it's a real supermanifold, okay, so yeah, but we have done also for complex supermanifold too, okay, yeah. Yeah, here is just a real 3-2 supermanifold, okay. Now, it turns out, okay, so first you promote the gauge field to become really a one forms, okay, and the second thing is you promote the lambda, the gaugino, to become, again, a superfield. Namely, this is just a one form superfields, which has an index here. So this means that also this object has the first component, which is just the gaugino, but then of course there is the expansion of thetas, okay, the expansion of thetas. And then it turns out that you can build an action, R32, written in terms of this quantity, A and W, okay. Okay, the different representation is the following. Okay, usually you do the following. You take all the component, okay, of the spectrum. Usually you put inside of some superfields. Okay. This framework here, you take all the degrees of freedom and you promote it to becomes a superfield. For example, the gauge field becomes a superconnections. The Glugino becomes a superfields of this type. Now there is a geometric formulations constructed by people in Torino and other people, which is known as rheonomic constructions, that allows us to build an action. Okay, and this action has all these good properties. But it's built in terms only of, let's say, forms and differential of forms. They never use Hodge dual, okay, but okay, you can also use the Hodge dual in this framework here. But it turns out, for example, that this action is closed, okay, and this is closed because of the properties, for example, now, if you do the following, of course, you increase the number of degrees of freedom, okay? Because, of course, all these fields has an expansion of, and gives a lot of components. So therefore, in order to get the correct number of degrees of freedom, you impose some constraint of the superfield. Those are the usual conventional constraints, okay? And it turns out that this condition is equal to 0 on these constraints. In their language are called as rheonomic parameterizations. Okay, the rheonomic parameterizations are the usual constraints. Okay, now once you have this action here, okay, you can build now a corresponding action here S, okay, which is just the integral of 3 is 2, okay, and then here the 3 is 0, and A and W, okay, times this picture change operator 0, 2. Okay. Now, it turns out the following, that when you choose, for example, the picture change operator, the first one that I show you, that one, let's say the trivial one, this gives you the component action. It gives you the supreme means in 3 dimensions n equal 1 in component action. Okay? However, if you change this picture change operator and you require that it respects some isometry, for example, it respects supersymmetry, you can build an object which respects manifestly supersymmetry, you end up really with the superspace action. Okay? So it gives you the superspace. Namely, this object is a rather redundant formulation of the supersymmetric models, but it contains in several ways all possible superspace representations. Okay, namely any superspace formulation of the same theory can be reached in this way just by changing the picture change operator. Okay, let me give you an explicit example now. Okay, let's consider, for example, Supergeometry. Okay, now Supergeometry it's an even simpler theory. And I can write down for you the complete action, which is the following. L30, okay, is as the following form, is A dA plus 2/3, there is a trace, okay, A wedge A, plus 1/2 of W square, okay, times the volume, the 3-dimensional volume. Let me use I use this notation VA to denote the supersymmetric Vierbein, theta, gamma d theta. Okay, these are the gamma matrices in 3 dimensions. And so here I can put a V3 times 3 factorial here in this way. And there is a trace also here. Okay, so this action here has the properties, okay, the property that it is closed, okay, is equal to 0. If you go to the component action, this gives you the component action, 3/0 in component action gives you exactly trace of ADA plus 2/3 of A wedge A, plus the fermionic mass terms, okay, times, let's say, D3x, okay, in this way, okay. Maybe over factor 2 here, okay. However, if you choose another picture change operator, and the other picture change operator is the following, which is 0, 2, which is actually VA wedge VB, and then there is epsilon A, B, C, derivative with respect to theta, gamma C, derivative with respect to D, of delta of d theta alpha, wedge delta of d theta beta, So if you write down, and this is just a derivative of the argument of delta function in this way, okay? So this picture change operator, it is manifestly supersymmetric, okay? And you see the following, that when you insert this picture change operator in the action in this way, okay? So it gives you automatically, not the component action, but gives you automatically the superspace action, okay? The usual superspace action for Superchern-Simon theory. So what actually we found out, we check for let's say for several models, for example, for Vesu-Minovit model for dimension, super-Hamilton for dimension, super-Hamilton for dimension n equal 2, supergravity n equal 1 and n equal 2, always works down. You can write down the action in these beautiful forms where there is an integral of a supermanifold of some action of this type. Yes?
So I'm a little confused because you said that the action is independent of the choice of y. Now you're saying that everything conforms.
Well, the action, I mean, the choice of y's, it gives you the representation of the action. Namely, all the actions are equivalent in the sense that they are different superspace realization of the same theory, okay? So all these theories are equivalent. Okay. No. The field theory is content is just. I mean, it is the equivalence between the action in superspace and the action in component. Okay. Namely, the action in superspace. Of course, if you perform Berezin integral, you get the action in component. Okay. So it's the same theory, of course, but written in different language. One language is the superspace language. The other language is just the component action. Okay. Now here, essentially, by using this picture change operator, okay, you can write down any let's say realization, any superspace realization. For example, if you write down harmonic superspace, you can also do it in this way, okay, and automatically give you the action in the harmonic superspace. Or sorry? Oh, well, in this case, are equivalent. Okay. Yeah, the equivalence is because actually this object is defined up to the exact terms, okay? So if you're able, if you change the y by exact terms, because this object is closed, then automatically equivalent. However, it turns out that this actually works. There is a common law that in this Raanomic approach, the action is closed. It is closed if you have auxiliary fields. Okay? If you don't have auxiliary fields, then the action might be closed, okay, or not. Okay? It turns out that even in the case where you don't have auxiliary field, if you write down these expressions, okay, it gives you at least, for example, for n equal 1, d equal 10 super-Hamilton, it gives you the closest things to a supersymmetric formulation, which is just the pure Spinors formulation of super-Hamilton. And this also works for 11-dimensional supergravity, for example. That gives you the closest things, okay. Even though you are not allowed to do it, because you cannot change it from this, because there is no close action occurring. So, of course, this is just a top form, so it transforms as a super deformism in the right. It's just a super differential form, so it transforms as a differential forms under diffeomorphisms. Okay, and actually, if you want to see how supergravity works, namely how recover the supergravity transformation of this part, okay, you have to study what are the supergravity transformation of these picture change operators. Okay, and what you're able to see, indeed, actually how actually you can impose the condition in such a way that gives you really the supergravity action correctly. Okay. Sorry. Yeah, this transform as C0 to integral forms, okay, and you know geometrically how this transforms correctly. Yes. Okay, so of course it depends what you actually require for this y, for example. So namely, if you require just some isometries, of course there is a certain set of this. Okay, we have not explored, so we know that in some simple case there is a classification of this. Okay, but we have not explored in general, indeed. Actually, one actually should indeed try to understand what is the cohomology H02, for example, of this supermanifold, and then try to see if they are indeed equivalent. And this is certainly quite interesting things. Okay. Let me now do the following. Okay. Now let me write down the action in the case of Chern-Simon. In the case of Chern-Simons, the action turns out to be the following. Okay, so here you have these expressions. So you trace ADA plus. Let me do it abelian because it's a little bit easier. I don't want to stress about discuss the interaction terms at this moment. Okay, then I will do it. I have this object, and then I put this picture change operator 0,2. Okay. Now, you can do the following. Okay, you can ask yourself, okay, but this is the most general expression they can write down. So you see, it is factorized. There is a 3-0 form and 0,2 forms. Okay, is this the most general one? Okay, can I do something better? Please notice the following: that this object, indeed, as I wrote before, can be written as a product of two, 0, 1, which is along the direction theta 1, times 0, 1 along the direction theta 2. Let's put 1 and 2 here, okay? So namely, the first picture change operator that I wrote actually was factorized into picture change operator. Indeed, actually, you can do the following. You can always factorize up to exact terms. Okay, so that's actually something that we did with Carlo. So indeed, you can see that every picture change operator can be factorized in the product of two. Okay, so once you put here, the exact terms drops out, and then you can see you can bring this to picture change operator inside of the action, and you can rewrite this expression this way: 1a wedge d of y2a. Plus, and also I can write down like a yw and y2w times v cube and 3 factorial, like this. Okay. So I did the following. So I brought this picture change operator close to the gauge field. Okay, I multiplied this, and then you see that this object now becomes a 1-1 form. Okay, a 1-1 form. This also becomes a 1-1 form. Okay, and it also becomes a 0-1 form, okay, and then wedge some 0-1 forms, okay. So the idea is, well, can I do the following? Can I rewrite this action in the following way, like a 1-1 form, d of a 1-1 form, okay, plus a w, which is a 0-1 form, wedge 0-1 form in this way. So again, writing everything, okay, here there is a V3, okay. Writing everything in terms of differential forms without considering this a factorization, okay. Now, together with the student, we show indeed that if you start from these very general expressions, okay, please note that this expression is very interesting because it shares a lot of similarities with the superstring field theory. First of all, because this object A11, if you expand in component, being a picture number 1 forms has an infinite number of components. Okay, so if you expand this object, so A11, this has an infinite number of components because you can expand first. The first things you can do is the following: you can expand. So a function x and theta, and then you expand like a dx, okay, with some index here. But then you can do the following: you can multiply by d theta 1 to some power, and then you can multiply by delta functions, derivative of delta function to the some power of delta 2, okay? Of course, you can do also in the reverse way, okay? So there is an infinite number of component, p goes to 0 to infinity, of these types. This is not the only case. There are other 3 sectors, indeed, of infinite number of terms. So these actions share a lot of similarities with superstring field theory, namely, this object contains an infinite number of components, okay? So with the student, we check the following. We check that if you calculate the equation of motion of this action, you go back to the equation of motion of a really Chern-Simon, okay? So namely, the equation of motion up to gauge transformation are really the usual Chern-Simon type of equation of motion. Okay. The second thing is, how can I write down interaction here? Okay. How can I write down interaction here? Here, the problem is that if I try to write down interaction like a 1-1 wedge A11 times wedge A11, Here I'm running into some problems, okay, because this has 3 delta functions, okay, but 3 delta function because of antisymmetric property cannot write down here. So I have to do something, okay. So what can I do? Well, I have to introduce here another picture change operator, which instead of increasing the picture, which means multiplied by delta function, should remove the picture, okay, should remove delta function, okay. Indeed, in this framework, there are again 2 picture change operator. One picture change operator, which I told it is y, which map along this y1 and y2, for example, which maps along these directions, okay? But there is another picture change operator which increases the pictures, okay? Has a quite interesting structure, okay? But this object indeed decreases the pictures. You can apply this picture change operator to this object, and indeed removes the delta function correctly, okay? And then you can try to build interaction terms, okay? You can try to build interaction terms by do the following. First, you multiply 2, and then you apply the picture change operator like this, or as we learn from your work, okay, you can do the following. You can first lower the picture, for example, like z of a11, and then multiply by the product of this, okay? Actually, what we learn also from your work that there is one way to write down in a cyclic way, okay, and in such a way that you can build somehow interaction terms of these types. So it turns out the following, that indeed this Supergeometry action with the interaction can be written in the same way as the superstring field theory with the A infinity structure. Namely, the first terms that you can add here to this action is just these triple terms, these interaction terms of this type here. Indeed, actually, to be precise, as this form, like this, and then there is A11, wedge z of A11, wedge A11, okay? Now, of course, by cyclic, you can rewrite this expression here. And it turns out that this gives exactly the same structure as in A infinity algebra. Namely, this gives you a 4-point interaction terms that actually allows to build all the other multi-product in the same way. So, indeed, actually, in the Supergeometry model in 3 dimensions turns out to be quite interesting because it shares a lot of properties as in A infinity superstring field theory, but actually the calculation is much easier because it's done in quantum field theory instead of in string theory or string field theory. Okay, it is interesting that you can formulate it in this way. So. Let me just 2 words how this picture change operator Z works. This picture change operator Z works in this way. Okay. Now, so in this space we have some delta functions, d theta of alpha. Okay, and then what I want to do is want to build an operator which removes delta functions, okay? To do that, you observe the following. Suppose that I consider a vector field which is a not vector fields, okay? The easiest way to do is a not vector fields of this type, theta alpha, okay? So this is where d alpha are constant coefficient, okay? So this is not vector fields, okay? Once you have a not vector fields, you can build the contraction along this vector field. This is the contraction along these odd vector fields, which has the property that is not an anti-commuting operator. Namely, d square of this, it is not 0, okay? So, but then in terms of this operator, you can build the following quantity. First, you can consider the delta function of this operator, and you can use for this an integral representation. We use that following integral representation, okay? And also you can build theta of this, the Heaviside theta function, which is this object, d theta e to the id t plus I epsilon, okay? These 2 operators, okay, are 2 differential operators acting on the space of these integral forms, okay? And indeed, actually, if you apply this operator ed to delta of d theta alpha, you do the following. Integral, then you have dt, e to the it id, acting on delta of d theta alpha. Okay. Now, this object here actually does the following. It actually translates along this direction of d theta. So the action of this operator acting on delta function, you can rewrite this object as delta of d theta alpha plus id alpha of t. Okay. And then once you arrive at this point, you just integrate with dt, but this is delta functions. Okay. So the calculation gives you, I think it is I over d alpha, the calculation gives you this object, okay? So if you act on this direct delta function, acting on this quantity here, it gives you just a number. So it removes the delta functions in this way. However, if you do it, if you act with the theta, okay, act with the theta, it gives you something interesting. Let me do it. So if you act with the theta of id acting on the delta function of d theta alpha, okay, you perform just the same calculation and you get I of d theta alpha, okay? So you get the inverse of d theta alpha, okay? So those inverse of d theta alpha actually were introduced some times ago, but together with Simone, Noia, and Catenacci, actually, we formulated in a shift theoretical point of view, and namely, so we give somehow a meaning. This object has to be understood as a distribution of valued type of forms, okay? At the same level of delta of d theta alpha is distribution type of forms. This is also a distribution type of form known as the principal value of this object, okay? So we recover the distributional property from a shift theoretical point of view, which is quite nice properties, okay? And once you have this object here, you can build the picture change operator as much as in string theory. You just calculate quantity of this type. And then, well, so we perform the calculation using this quantity here, acting on superforms, acting on a different type of integral forms, gives you a consistent way to do the calculations, okay? So, yeah, I think that's quite amazing how the geometrical picture works, okay? And so we are planning now to first to clarify some mathematical issue related to this inverse form, and some mathematical issue related to this space of picture number one forms, namely this type of complex is somehow mysterious how this works, okay? The reason why there is an infinite number of delta terms in each of these spaces, so it is unbounded from above, unbounded from below, and each of these spaces are infinite dimensionals, okay? And the reason is that in order to take care of the covariance of the theory, you need infinite number of terms in each of them, okay? Still, from mathematical point of view, we have not understood that particular complex, so it's still to be clarified, okay, how it works. But I mean, at this point seems to be consistent, and we are able to reproduce what you did in the case of superstring field theory in these purely geometrical settings, okay, without, okay. Sometimes, when actually I want to check some of this relation like this one, I use conformal field theory, okay, in order to see indeed actually if I get the correct calculation. But every time I did with the conformal field theory, I can always reproduce by just using supergeometry, okay. So I think I will stop here. I'm happy to answer questions. Thank you very much. Yeah.
So your picture number minus one action. So is it? So now you have an infinite number of fields, right?
That's right. Yes. Yeah.
So now it's not equivalent anymore to the factor.
Yeah. Exactly. So what actually we check at the moment is that the equation of motion are equivalent, okay? But the level of action, I don't really know how to prove the equivalence, okay? So certainly you can do something like choosing a gauge, okay? Choosing a gauge, which means choosing the particular factorizations and then going back to the original action, okay? But so I don't know actually. Indeed, when you have interactions, namely when you have the interaction, you have the full systems of interaction terms, then I don't know if it's just filler definitions of the original one or if it's something new, okay, that's, I don't know.
So in this picture minus one approach, is it helpful in some way to have all these other fields?
It's a?
Is it helpful to you to have all these extra fields?
Yeah, the idea is that indeed, actually, if you do the calculation from really from quantum field theory point of view, okay, and indeed you have this picture change operator, because of this representation, for example, you end up with some divergences. In the same way as in string theory, you have the colliding pictures, which gives you some divergences. So once actually you start doing the first interaction term in this way, then automatically you're forced to add these other terms, otherwise it's not normalizable. So
Okay, maybe I wasn't clear. So I'm asking whether, so now in this picture minus one formulation, you have an infinite number of component fields.
right. Yeah, that's right.
Is it helpful to you to have an infinite number of component fields for silencing?
I don't know, it's, I don't know how to answer. Yeah, I think it's nice because you can somehow study this model from this point of view, okay? And one thing is try to understand if it is equivalent or is just, which is not the field of definition of the original theory. That I think so, yeah. Yep.
So the feature changing operator in string theory, that D is like the RC operator, and then all this
Exactly.
D is beta field.
Exactly. If, yeah, okay, in the language, it's just the number of delta function counts the picture. So increasing the number of delta function means increasing the pictures. If you look at from a string theory point of view, when actually you bosonize or fermionize, the delta is I to the minus phi, okay? So usually it is just a reverse, namely the picture number is just the reverse what we did actually here, okay? This is just the, yeah?
Work with the complex supermanifold.
Yes? Yeah. Indeed, actually, Simone Noia is expert about non-split supermanifold, non-projected supermanifold, okay? And so we apply this, namely we studied, okay, the complex superform in that particular framework, namely some of the idea, for example, so together with Simone, actually, we represented those objects as some specific sheaf of this space, and therefore we know actually how to transform even in complex. For example, we did it for complex superprojective spaces, for example, and there we know how even for non-projected ones or non-split ones it works. Okay, namely, in some sense. Oh, yeah, sure. No, let's say what we did was just only studying the integral forms in that framework, but not right down in the Lagrangian in this framework, yes. Yeah, that would be quite interesting to see, yes. Yeah.
We try to apply that to some, when we use Non-assoc,
yes.
one way to pursue here, which is content, you write the top form using Socrates, you use the fact that then if you do Socrates in three dimensions and zero,
Yes.
and this is the way you can try to constrain quantum time.
Yeah. No, here actually you can use the powerfulness of this geometrical approach. Okay, so one application that we did was the following. Sometimes ago there was this work doing this multi-Vierbein gravity. Okay, and multi-Vierbein gravity is built in this way. So you have a multiple action of Hilbert-Einstein type for each graviton. Okay, and there is the interaction terms which it is of the cosmological type of terms. Okay. Which is just, okay. Now you can do it the same game using just this supergeometry approach. Now, then you know that you must write down in integral forms, okay? So what you can do, so we generalize this expression. So what you're asking me is now, now here you have some supergeometrical criterion, like write down this as an integral forms for a given space, and this gives you a constraint on the possible counterterms that you can add to the theory. Yes, yeah, we can do by gravity, by supergravity indeed, in this framework. Yeah. Exactly. Yes. Yeah. This is just the criteria how to use these integral forms. Okay.